We are going to learn an existing method called EasySum. It's a systematic way to work with whole numbers, create sets, and perform simple arithmetic operations to arrive at a final total. First, we select a whole number as n. For this example, we'll take n equals 21. Next, we create a set of whole numbers starting from n and going down to 1. First element of set n becomes the numerator. Now we choose denominator as m, which must not be 0. So let's take m equals 6. Then divide n by m and take the remainder as r1. For 21 divided by 6, the remainder is 3. Now we create a new set Q with n empty spots. Replace R1 in the first spot. Next, we take the second element of P, n minus 1 equals 20 as the new numerator. Divide 20 by the same denominator 6. The remainder here is 2. Replace R1 in the second spot of Q. We continue this process until all elements in set P become empty and set Q is completely filled. Finally, we add all the elements in Q, so total is 21.
You are given an array A with n integers. The task is to calculate the sum based on all unique pairs of elements I and j in the array where I is less than j. These are the constraints you should follow. For each pair ij, you should first calculate the value of flow by the equation ai plus aj over ai into aj. And then you should add the integers values to the total sum. Finally, return to the total sum for the array. Now let's calculate for the example 1, 3, and 5 array. First, we identify pairs 1, 3, 1, 5, and 3, 5. For 1, 3, it is 1 plus 3 over 1 into 3 equals 4 over 3, which rounds to 1. For 1, 5, it is 1 plus 5 over 1 into 5 equals 6 over 5, which rounds to 1. For 3, 5, it is 3 plus 5 over 3 into 5 equals 8 over 15, which round to 0. Therefore, now the total is 1 plus 1 plus 0, which is equal to 2. This method efficiently processes arrays while following the necessary constraints. Today, we are solving a power calculation problem where we need to find the last two digits of a large sum. Imagine you have two big numbers, k and n, and you are asked to calculate the sum of powers. The numbers get really big, so we can't calculate them directly. We only need the last two digits, which is where modular arithmetic helps. By using modular exponentiation, we can find the remainder when divided by 100, and that gives us the last two digits. Here's how we do it. We start with a sum s equals 0. For each number from 1 to k, calculate that number raised to the power of n and take it modulo 100. Add the result and then modulo 100 for the final sum. For example, if k equals 3 and n equals 2, the sum is 1 plus 4 plus 9 equals 14. The last two digits are 14. In summary, we use modular exponentiation to quickly find the last two digits without dealing with large numbers.
Let me explain this interesting problem. We are given three numbers respectively. C is the starting value, M is the modulus, and N is the number of vectors. The goal is to calculate how many distinct residues appear is scalar products of these vectors. Here's how this works. First, we generate the sequence using the formula as shown. AI plus 2 equals AI plus 1 plus AI mod n. For example, if C equals 3, M equals 5, and N equals 3, the sequence becomes set as A equals 03314 Next, we form n two-dimensional vectors by pairing terms like v1 equals 31, v2 equals 40, and v3 equals 44. Then we calculate scalar product of these vectors modulo v1 dot v2 equals 2, v1 dot v3 equals 1, and v2 dot v3 equals 1. Finally, we collect the distinct residues. In this case, 1, 2. There are two distinct residues. And that's the answer is 2.
Today, I am going to explain the problem of calculating the summation of sequence and then taking modulo 10 to the power 9 plus 7. Let's break it down step by step. We are given two numbers, n and k. N is the number of terms in the sequence. K is the power to which each number in the sequence is raised. We use the formula Tn equals to 10 to the power k to create the sequence. For example, if n equals 5 and k equals to 2, the sequence becomes T1 1 to power 2, T2 2 power to 2, T3 3 to power 2, 2 4 4 to power 2, and also summing in next, we calculate the sum of all terms in sequence. Sn equal to T1 plus T2 plus T3 plus also T1. For this example, S5 for 1 plus 4 plus 9 plus 16 plus 25 equals to 55. If Sn is very large, we simplify it using the modular operation. Sn mod 10 to the power 9 plus 7. The modulo operation gives the remainder when n is divided by 10 to the power 9 plus 7. In this case, 55 mod 10 to the power 9 plus 7 equals 51, since the number is small.
Let's talk about series in mathematics. The series is the sum of the terms in a sequence. For example, the sequence 1, 2, 3, 4, 5 forms. But the series 1 plus 2 plus 3 plus 4 plus 5 equal 15. There are three key types of series. The first one is arithmetic series. Consecutive terms have a constant difference like 1, 3, 5. Its sum of the formula is Sn equal n by 2 into the bracket a1 plus an. Second one is geometric series. Terms have a constant ratio like a 2, 6, 18 with Sn equal a into the 1 minus r power n close the bracket divided 1 minus rn. Third one, harmonic series. A is sum of the reciprocal like 1 plus 1 over 2 plus 1 over 3. Studying series help us uncover pattern, model real-world phenomena, and solve puzzles. For the example, infinity series like 1 plus 1 over 2 plus 1 over 4 coverage 2 factorial.
Let me quickly explain the circle summation problem. Imagine we have n students sitting in a circle, each with a number assigned to them. The goal is to update these numbers over m rounds, following a simple rule. Here's the rule. In each round, we start with one student. Their number is updated by adding the numbers of their two immediate neighbors, the one clockwise and the one counterclockwise. After updating one student, we move to the next one in clockwise order and repeat the process. For example, if we have 5 students and their numbers are 10, 20, 30, 40, and 50, we start with the first student. Their new number becomes 10 plus 50 plus 20 equal 80. Then we move to next. We repeat this process for all the students in the circle and for all the rounds. By the end, we get the updated numbers for every student. This problem is about understanding how the values evolve based on their neighbors in a circle arrangement.
So let's move on to counting equations. You can see the procedure is going like this. The answer is an equals n minus 1 and x is equals to 1. So the n is represented from 1 to 5. So let's move on to the function. A1 is multiplied by x and A2 is multiplied by x. So likewise, it's going up to an multiplied by x. So at the last result is b. So the steps according to 1 to 5, b1, b2, b3 is representing. So if the n is equal to 1, you can see in the example, a1 is multiplied by x, so the result is 0. So likewise, the process is going like that. At last, you can see the results, b1 is equal to 0. After b1 plus b2 is equal to 1. So likewise, the steps are going that.
Let's break down XOR logic in a minute. Suppose we have an array set A equal 3, 5, 2, and 8. Step 1. Convert each number to binary. 3 becomes 0, 1, 1. 5 becomes 1, 0, 1, and so on. Next, initialize an XOR accumulator x to 0. Why? Because XOR with 0 keeps value unchanged. Now, we XOR the binary numbers step by step, starting with x equals 0. And the first element 0, 0, 0 XOR 0, 1, 1 is equal to 0, 1, 1. Next, the result is XOR with the second element. 0, 1, 1 XOR 1, 0, 1 equals 1, 1, 0. Repeat for all elements. At the end, binary is 1, 1, 0, 0, which equals to 12 in decimal. This cumulative XOR 12 is your final answer. And that's how XOR logic simplifies calculations.
To solve this problem, we start by identifying Qn as n into n plus 1 and Pn as 1. This makes the series sigma 1 over n into n plus 1. Using partial fractions, we decompose 1 over n into n plus 1 into 1 over n minus 1 over n plus 1, which allows us to rewrite the series. When expanded, most of the terms cancel out. Then only the first term and the last term remains. As n goes to infinity, the last term goes to 0. So the sum converges to 1. Finally, we express the result in modulo form. Since the sum is 1 and 1 into 1 is equals to 1/9, the modular result is also 1. Therefore, the sum of the series is 1.